Welcome back to Mathematics Lifeline. In today's video, I want to discuss two ways we can approach infinite limits. So I'm going to discuss the systematic degree rule and the visual degree rule. Now, I put this in air quotes because that's kind of what I like to call it, because really, with this one, you can just look at the problem and you can see what the answer is. And I love it, but the problem is it usually doesn't fly on quizzes and exams. So the systematic one is very important to know. We need to know how to approach these in a way that works for every single type of question. That way you can't get tricked, right? Um, so yeah, I'm going to go ahead and show both of these methods using three examples. I'm actually going to keep the examples the same so that we can show that we actually do get the same answer with these two methods. So without further ado, let's go ahead and just get started. Okay, so the first method I want to show is the systematic degree rule. So we're going to take the limit as x goes to infinity of x plus 8 over 2x squared minus 7. Now, what we're going to do is we're going to, and for both of these methods, we need to do this. We need to look at what the degree of the numerator and denominator is. So it's very important that the numerator and denominator are both polynomial functions. That way we can do these methods. If they're not polynomial functions, these limits do get a little bit trickier. But in this case, we have two polynomials, right? We have a line and we have some quadratic, right? So let's go ahead and see what their degrees are. So remember, the degree is the highest exponent of x. So in this case, the exponent of x is 1 in the numerator, and then in the denominator, the exponent of x is 2. And we're only concerned with the highest degree that we see. Now, in this case, the highest degree is in the denominator, and we know that that degree is x squared. So the highest degree is x squared. So the systematic way to approach these questions is we're going to divide every single term by an x squared, or the highest degree, right? So for this example, this is going to be the same as the limit as x goes to infinity of. Now, we're going to divide everything by x squared. So we're going to have x over x squared plus 8 over x squared over 2x squared over x squared minus 7 over x squared. So you see, we're dividing every term in the limit by an x squared. So now the next step that we need to do here is we need to cancel some stuff out. So the easiest one to see is with this 2x squared over x squared. Of course, this is going to cancel with that, and we'll just be left with 2 there. Now for the 8 over x squared and the minus 7 over x squared, there's nothing we can really cancel, right? Because there's no coefficient for the x squared, and there is no x in the numerator, so there's nothing we can do to help those. This one we can simplify. So if we have one copy of x in the numerator and 2 in the denominator, then when we divide those, we're just going to have an extra copy in the denominator. So this is going to be the limit as x goes to infinity of, this will be 1 over x plus 8 over x squared over. Remember, the x squareds cancel, so we just have 2 minus 7 over x squared. Okay, so now we're able to take this limit directly. And the reason why is because these functions now have a degree of x in the denominator. Remember, x is what is changing. X is what is approaching infinity. So if we just have a number in the top and an x in the bottom, any degree, we're able to take these limits. Because when you plug in infinity here, that means the bottom is getting bigger and bigger, right? So if the denominator is getting bigger, the fraction is getting smaller. So anytime you have something like this where it's a fraction over x, these are all going to go to 0, no matter what it is, because as the denominator gets bigger, of course, the whole fraction is going to get smaller. So when we take that limit, we're putting in infinity, so we really just have 0 plus 0 over 2 minus 0, which of course is 0 over 2, or 0. So that is our answer for this limit. This function will approach 0 as x goes off to infinity. So let's go ahead and do another example of this systematic degree rule. So we'll start that right now. Okay, so here is example number 2. This one is the limit as x goes to infinity of 4x squared minus 3x over 3x squared plus 7. So just like the last time, we're going to look at the degrees of these polynomials. So the degree of the numerator is 2 because we have an x squared, and the degree of the denominator is also 2. So we have an x squared here in the denominator too. So these are the highest degrees. So because they're equal, we're going to do the same thing. We're going to divide every single term by the highest degree. And in this case, the highest degree is equal to 2. So we're going to divide every term by x squared. So now we're going to have the limit as x goes to infinity. we're going to have 4x squared over x squared minus 3x over x squared over 3x squared over x squared plus 7 over x squared. So again, we need to do some simplifying here. So the 4x squared over x squared, of course, these are going to cancel. Same with this one. Now, this one isn't going to change, but this one we have an extra copy of x in the numerator and 2 in the denominator. So eventually we're just going to cancel this one out and only have 1 in the denominator. So when we rewrite this limit, we're going to have the limit as x goes to infinity. So this is just going to be a 4 minus 3 over x over. This one is just going to be 3 plus 7 over x squared. Okay, so the same kind of idea here. Now remember, just like we talked about last time, we can take this limit now because we just have these fractions or coefficients. So if we're having the fractions with the x in the denominator, this is going to go to 0, this is going to go to 0. So all we're left with is 4 minus 0 over 3 minus 0, which of course is equal to 4/3. So that means that the limit of this function as x goes to infinity is equal to 4/3. Okay, we're going to do one more example for the systematic degree rule before we move on to the next one. And for this one, feel free to pause and try it yourself. This one is going to be a little bit different though, but if you can figure it out, that's great. So let's go ahead and do that right now. Okay, so here we have the limit as x goes to infinity of x cubed plus x squared minus 1 over 14x squared minus 8. Now, like I said, if you want to try this, of course, feel free to do it, but this one is actually a little bit different. So if you don't know what to do, if you get stuck, then of course I'm going to be doing the solution right here. So pause if you want to, but if not, I'm going to go ahead and get started. So we're going to start this the same way that we do all the other ones, right? We're going to look at the degree of the numerator and the denominator. So in the numerator, we have this x cubed. That's the highest degree up there. But in the denominator, we have x squared. So in this case, the degree of the numerator is greater than the degree of the denominator. And when that is the case, we're going to divide everything by the highest degree in the denominator only. We're not going to divide by what's in the numerator, and we would have some problems. So that's why I worry if you paused, you might end up with an issue if you divided by x cubed. So in this case, we're going to divide everything by x squared. So let's go ahead and do that. So we're going to have the limit as x goes to infinity of x cubed over x squared plus x squared over x squared minus 1 over x squared, and all of that is over 14x squared over x squared minus 8 over x squared. Okay, so we want to do some simplification again. So this is pretty standard practice at this point, right? These will not reduce at all. These will, and so will this one. So we're going to have the limit as x goes to infinity. X cubed over x squared is just an x, plus x squared over x squared is 1, minus 1 over x squared, because that doesn't go anywhere, over this, the x squared will cancel out, so we'll just get a 14, and then we have that minus 8 over x squared that doesn't go anywhere. Okay, so now when we take the limit as x goes to infinity, these two right here are just the same thing. They're going to go to 0, they're going to go to 0, right? Both of those fractions go to 0. The difference is when we plug in infinity here, right? So this is going to give us infinity plus 1 over 14 minus 0, right? And of course, infinity plus 1 is still infinity. And when you divide that by 14, it's still infinity. So this limit will actually go to infinity. So that's one way to do this question. Now, I know it's a little bit weird because this is not the same method that we used for the last one, because the degree of the top is greater than the degree of the bottom. There is another way we can work with this though. If we still want to worry about the degree of the top and the degree of the bottom, what we're going to do is we're going to use some logic with limits here. So the reason we look at the highest degree is because they're the ones that change the fastest, right? We know that if we cube something, it grows faster than if we square that number, right? And so on and so forth. So we're just worried about the highest degree terms. So that ultimately means that in this case, the only thing that matters is this x cubed and this x squared, right? This x squared doesn't matter, the 1 doesn't matter, and the 8 doesn't matter. None of those matter. So we can really just look at the limit as x goes to infinity of x cubed over 14x squared. Because these are the only terms that matter, right? And we can actually simplify this, right? So this is the limit as x goes to infinity. X cubed over x squared is just an x over 14. And of course, we could see here that as x goes to infinity, we're going to get infinity over 14, just like we had right here, which gives us infinity. So there's two ways to go about getting this answer when the degree of the top is greater, right? This is the more systematic way. In a second, I'll show you the visual way, which of course you're going to know what to expect. But yeah, so this is the systematic method to do these limits of ratios of polynomials as x goes to infinity. So now I'm going to go ahead and introduce the visual way. So I'm going to start by showing a couple of cases, and then we'll get right back into these same examples. So we're going to go ahead and get started with that right now. All right, so now we want to talk about the visual degree rule. So I call it the visual degree rule because you can really look at these problems and immediately see the answer. So it's very, very useful. However, like I said at the beginning, oftentimes you're not going to be able to use this on a quiz or a test, but it's a great way to check your answer. So we're going to go over this anyway. So there's three cases for this, and they all depend on the degree of the numerator and denominator, or I call them the top and the bottom here. So in case one, if the degree of the top is greater than the degree of the bottom, then the limit goes to infinity. And case two, if the degree of the top is equal to the degree of the bottom, then the limit is coefficient 1 over coefficient 2. Now, I want to do a quick little example of this one because this gets confusing for people, especially when you first see this. So let's think about the limit as x goes to infinity of, let's say, x squared plus 7x minus 4 over 2x squared minus 4x plus 3. Right? I just came up with this example, but we see that the degree of the top is equal to the degree of the bottom. So when I say that the limit is equal to coefficient 1 over coefficient 2, we're looking at the leading coefficients right here, right? So we're looking at the highest degree terms. So this one is going to be a 1, this one is going to be a 2. So that means that this limit is just equal to 1/2. And you can kind of do this the same way I talked about at the end of the last example, right? Because again, the only thing that matters is the highest degree terms. So we can really get rid of this and get rid of this. So we just have the limit as x goes to infinity of x squared over 2x squared. And of course, these can cancel out, right? So we're going to, of course, get 1/2. So you're kind of doing what we're doing here with the systematic way. It's just this way you can look at this and immediately tell without having to rewrite anything that it's just 1 over 2, right? So that's what makes case 2 so nice. But yeah, so that's case 2. Now case 3 is if the degree of the top is less than the degree of the bottom, then the limit is equal to 0. So of course this always works as long as you have a ratio of polynomials. So now I want to go ahead and go back to the examples that we just did and show that we get the same answer with both of these methods. So let's go ahead and start on example 1. Okay, so here's our first example using this visual degree rule. So we have the limit as x goes to infinity of x plus 8 over 2x squared minus 7. Now again, we did do this example earlier, but it's important to make sure that we get the same thing. So we want to look at the degree of the top and the degree of the bottom, right? So in this case, we have the degree of the top is equal to what? Well, we just have x plus 8, so the power of x is just a 1, so that means that the degree of the top is 1. And the same way, the degree of the bottom is, well, we have 2x squared minus 7, so the degree is that x squared, that's the highest one, so the degree of the bottom is equal to 2. So here's what we know. We know that the degree of the top is less than the degree of the bottom, right? And because we know this, if we go back to what I just showed you, this was case 3, which means that the limit as x goes to infinity of x plus 8 over 2x squared minus 7 will go to 0. And all we needed to see was that the degree of the top was less than the degree of the bottom. So that's why I call it the visual, because you can look at this immediately and say, okay, degree 1, degree 2. Well, degree 2 is bigger, it's on the bottom, limit goes to 0. And it works every time for these ratio of polynomials. So it's a great way to check your answer for the systematic way, especially if you don't really feel comfortable with it. But yeah, so let's go ahead and move on to example number 2. Okay, so here we have the limit as x goes to infinity of 4x squared minus 3x over 3x squared plus 7. Now for this one, I'm not even going to write anything down except for the answer because it shows the visual version of this. I don't need to write anything down to get the answer, and that's what's so nice about this rule. So we want to look at the degree of the top and the degree of the bottom. And we can pretty clearly see that the highest degree of the top is x squared and the highest degree of the bottom is x squared. So that means we have case 2 here where the degrees were equal. And remember, like the example I showed you, we look at the coefficients of the highest degree x term. So we have x squared here, we have x squared here. So the coefficients are 4 in the numerator and 3 in the denominator. And if you go back to earlier in this video, you'll see that using that systematic way, we got 4/3. Um, you could see how much quicker this is, right? We didn't have to do any work, right? The only thing you may have to do is simplify whatever answer you get. But other than that, there's no extra work that you have to do. It's literally just look at the coefficient and look at that coefficient, and you are completely done. That's what's so nice about this visual degree rule. So let's go ahead and do one more example for this video, and then we'll call it there. Okay, so here's our last example. We have the limit as x goes to infinity of x cubed plus x squared minus 1 over 14x squared minus 8. So again, we're looking at degrees here. So the highest degree in the numerator is 3. The highest degree in the denominator is 2. So in this case, we have the degree of the top is greater than the degree of the bottom, which was case 1 from our how we define this visual degree rule. So if we have case 1, we know automatically that this limit will go to infinity. Now, here's what's a little bit tricky about this one is there are times where you'll have the limit as x goes to negative infinity. And in that case, it's not always going to be infinity. It could possibly be negative infinity. And it really depends on the degrees of your polynomials. But for this video, I'm only going to focus on the positive infinity version. So we know from case 1, this goes to infinity, and that matches the answer that we got before. So this one, we have our own case for when the degree of the top is greater. So there's not multiple ways to do it. There's not really any way to mess it up, right? You see 3, you see 2. Of course, the numerator is bigger. It's going to blow up faster. It's going to go to infinity. And that's what's so nice about this visual degree rule. So yeah, that's all I have for you in this video. I hope this helped. Again, I love the second way, but the first way is very important to learn. And hopefully I helped you out with that. Of course, let me know if you have any questions, but if not, then I will see you in the next video. Thanks for watching.